We call our project Catch Me If You Can because that's the goal of this, to attempt to catch a golf ball, which we affectionately call Mr. T, because it kind of looks like, Mr. T, in a catcher down at the other end. And obviously in physics, this is the concept of projectile motion. Next. And this is the goal. You press on it. We actually took a video to prove that it does work. You're pen too far. Put the golf ball in, and when the catcher stops, it shoots, and it caught it. And that's the point. To shoot the golf ball at different angles, assuming that the velocity of the launcher is the same, then you should be able to calculate exactly where the golf ball lands. Next. And basically, this is the idea of projectile motion, that the horizontal component of projectile motion stays the same. It's basically a constant. The only thing that's changing is the vertical motion due to gravitational pull. And next. John's going to explain some of the.
Yeah, so Mike already mentioned what we have here. These are different types of projectiles. Anything basically that you throw is a projectile, so it applies to almost every sport I can think of. I mean, obviously there's some sports where you don't need to worry about projectiles, but I find the projectile motion as a teacher, students really, I guess, I don't know if I find it more enjoyable as students, but we do different things. Like normally we'll put a ball on a ramp and let the ball go down a ramp, and then they have to predict where it's going to land. And they give them a sheet of paper with a little target, and they got to get it there. And their lab is based on where they get, where they hit it, and they're like, well, that's not fair. I'm like, well, tough. So that kind of like, that led us into this, and we started. I'm glad we did this. Just trying to think. Okay, can you go next slide? Because okay, now the formulas you can't really see because they're in black, but basically the whole premise is that since the horizontal velocity is constant, it's simply the vertical velocity times time will give you how far the object goes, but we need to know the time. So to figure out the time, we know that the projectile, if it's launched from a certain elevation and lands at the same elevation, it's going to take so much time to get to the top, and then that same amount of time is going to take to come back down. So if we find the time to get to the top, multiply it by 2, we have the total time of flight. So if we solve for that, we get like this equation here. And then plug that back into the formula for the range, and you get a formula that which we used in a code. And we simplified it to the one that's in the bottom left-hand corner, using a trigonometric identity. So most people have seen that if you've taken a physics course to some extent. So next slide, please. These are the standards, which
these are the
New York.
Lucky you.
New Jersey.
These are the New York State physics standards, and these are just 4 of them that we have up. And you can see that projectile motion is an important part of the physics curriculum, and it's been around for ages. Next. And this is basically the launcher. We took a Wilson putting pal, which is this thing here, and we modified it by carving it up into pieces. And that became our launcher, which led to problems down the road. Basically, we started off with the simple putting return machine. You put the ball into the machine, it kicks it back to you. And that's what we used. There's a solenoid that pulls back a metal bar onto a spring, and when the current stops, the spring propels the bar forward, which launches the ball out. And we built a platform. Well, we didn't build. Alex built a platform for us that would allow us to raise this putting pal to pretty much any angle we wanted within a certain range. Next.
Basically, the platform and the cart have 2 things in common, and that's that we're using rotary potentiometers to get information about the angle. We're getting information about the angle for the ramp, and we're getting information about the position of the cart using that. The difference being that this one here is a single turn potentiometer. It goes from 0 to 100 kilo ohms. Whereas the other one is a 10 kilo ohm potentiometer, but it allows for 10 turns. So in designing this, we picked gears such that 10 rotations of the potentiometer would be long enough to go down the entire length of the track, so it wouldn't get stuck. So that was, on the next slide, but I'm getting ahead of myself. We used, yeah, that's what I just mentioned. Can you go back to the previous one? I'm sorry. We used a stepper motor that was provided with one of our kits, and we modified it just like on the Bobots. And that was fine enough to go up and down, had enough torque and enough speed. And Alex did a great job with building the track for us. Basically, if you look at this and you look at the inverted pendulum in the lab, you'll notice that they're very similar in design. We have one motor controlling the cart, and we have the two rails as support to let the block go back and forth. And inside the block, there are two linear ball bearings, which allow it to slide smoothly. And so that's all there is to that. Okay, next, and then after that. Okay, you wanna? Okay. Okay, everybody's used the basic stamp here, so nothing different. We're using 9 pins of the available 16 input and output. And yeah, performs basic mathematical calculations. That basic is really basic because, as we all know, you can't multiply decimals and all that kind of stuff. So in a lot of our code, if we had to multiply by, say, 1.1, we had to multiply by 11 and then divide by 10 to do the same thing. So that was kind of frustrating. And that leads to uncertainty in where this thing lands, where the range is calculated because of rounding. So for example, the range could be 70 centimeters, and we may have it go to 64 or 68 or something like that. So that's why if you notice, our target platform is a little bit, I don't say it's big, but it's not it's not small. It's, you know, it's not like it's not the diameter of a golf ball. Okay, we're not gonna, this is kind of like primitive technology, you know, with the old catapults and stuff. Like we're just throwing the ball out there. We have no idea where it's going. But that'll lead into some other interesting things. Next. Okay, here's our breadboard, which is attached to the back. And we're using 2 ADC chips over here, one for the ramp and one for the cart, like I mentioned earlier. Then we're using the beloved H-bridge here, which we spent a few days, right, Nathan? We used Nathan's original design, and then he told us, oh, you had to do it a different way.
No, that was a soldering iron.
Yeah, right. But I think we were the pioneers here, right, Mike? Yeah. Yeah, we did all the dirty work here. And I think you benefited, right, Bill? Because,
Oh, yes.
right, Bill benefited, so that's, I feel good about. I feel good.
Need the H-bridge for the DC motor to
Right.
lift it.
Yeah, we need
This is the
to.
servo, but that's the DC motor.
Yeah, basically, an H-bridge, if you don't know what it is, it allows you to take a motor and to have it turn one way and turn the other way, electronically. Okay, normally, if you take a motor and you hook up a battery to it, you hook up the positive to one end and the negative to one end, it'll spin one way. Okay, if you reverse the leads, they'll spin the other way, but you don't want to do that in an automated system, so you do it with electronics. Okay, and these are transistor diodes and resistors that are all part of that circuit. Okay, next slide. Okay, solid state relay is basically a switch, but it's just, well, it's solid state meaning it's electronic. So normally the way this thing operates, like Mike said, is, you hit a ball, and when the ball would go in, there'd be like this little clip in there that the ball would hit. The clip would activate as a switch. Okay, we wanted to use something electronic, so we went with a relay, which is housed in that little case there. Okay, next. Okay, so our experiment is you can choose an angle between 20 and 65 degrees, and we'll let you pick any one you want. But I won't guarantee it's going to work. We'll mention some things about that later. So the first thing is you enter the angle. The launcher will go to the specific angle. The cart will then go to the correct position. Then you're prompted to put the ball in the launcher, and then you press a button, and the ball will launch. Okay, and then the process is repeated. So let's go back, and we'll demonstrate that?
Yeah, well, no, let's finish it.
You want to finish? Okay.
And just basically the results that we found. Next. It was determined that the launcher is actually pretty accurate for angles from 20 to 30 degrees. Once you got outside that range, it became far less accurate. And the problem we thought was that at high angles, the motor was unable to sustain the velocity necessary to get the ball to where it's targeted. It was constantly short. So we used a formula and we put it in. Basically, we took the angle of the launcher minus 25, and that worked. And it worked pretty much for every angle up to 65.
I don't know what you call fuzz factor.
Yeah, fudge factor. Fudge factor.
You are probably reinventing without me telling you fuzzy logic.
Right. Yeah, and the key is that it works. And now it's pretty accurate between 20 and 65, we think. Next. And of course, there's uncertainty in this. The main one we mentioned is that the basic stamp 2 is unable to do floating point calculations, which means problems with the decimal point. And the rounding here can be a big difference in the ball landing where it should and not. And also, the main problem we had was that since we couldn't control the amount of voltage going to the solenoid, so we think we're getting different velocities ever so slightly, but it's enough to throw it off from landing there. And right, and the hinge at the back also, even though it seems to hold pretty well, as it stops, the hinge sometimes will come down or go up, and it really does not lock in at the specific angle. Next. This is our project cost. Minus labor, as Alex had brought up. And ours, believe it or not, came out to like over $200. And most of it was due to the materials required to build the ramp. It wasn't that the electronics. No, because that's not part of it. That has to be added in separate to get it to run. And next. And we have just some suggested projects people could do to finish it up. Maybe determine the relationship between angle of release and the launch velocity. Use sensors to verify the maximum height of the golf ball. And try to account for the discrepancy between the height and the catcher platform, because when this comes back, they're not at the same elevation. That's another uncertainty that's thrown into it. Next. And we want to
Just want to
see that.
like I also thought like if you were able to put throttle gates rather than as the ball launched, what the speed is, and have the catcher like it's going to be here already, but then if it yeah, make an adjustment to go back and forth. Ideally, it would be nice if you could have like a catcher as soon as the ball got out that was able to sense the ball and follow it. If you could find something that can be fast enough, but I'm not sure. You know, so it's kind of like basically run out the catcher. So almost be like a football player, like a quarterback throwing the ball to a receiver, like so.
And this is our this is our interview for a day, and we figured out that if you hit this, you get free tuition at college. So we have nothing to worry about.
Okay. So anybody give us an angle? We'll try.
Between 20 and 60.
Kevin knows.
45.
42 the number you want to put in?
No, you might say everything that's 65 is 65.
Can I set the angle? And before I made a slight adjustment here. So now I'll place the ball on here. And hit the button. Okay. The ball hit the catcher.
Hit the platform.
Okay. And we'll do it
Another
again.
angle? Anyone?
Whatever. Wait, fine, good. So anyway. Now, the thing is, like you say, well, it didn't move much. And that's because, like Mike mentioned, as the angle gets bigger, we reduce the range some, because we know that, like if I was to, like, I would take this with my students and have them figure out exactly what they need to do to get a better point. Right now, we just kind of like figure something out that works. But there's really no solid physics behind it. I would like them to like actually figure it out, because I think that as the ball is raced, the force that the solenoid will provide, I think it's changing only because it's I think the way the golf is sitting on it, so it doesn't have the same force. So I think